today it's about vacuum birefringence, and those of you who hear it for the first time, you might wonder whether how can vacuum be a birefringent? And of course, this will be my the first part of this talk. And if we talk about birefringence, then obviously we need to talk about polarimetry. In this case, about X-ray polarimetry, and this may also be new for some of you. As we worked through X-ray polarimetry, we made some, well, pretty nice advances. And so besides this heroic application of detecting vacuum birefringence, we also found a few more down to the earth, more immediate applications. I quickly review some of them. Then I will talk about limitations for polarization purity, which is of course of decisive importance, and then on an experiment at the European XFEL, and finally kind of an outlook, so telling you what it takes actually in order to measure vacuum birefringences. Now, to the first point, can vacuum be birefringent? And the thing starts with Dirac. As you all know, he devised his Dirac equation in order to make it relativistically correct, but he got more than he wanted. Well, perhaps he was quite happy to find the spin, but he was certainly shocked, and not only him, that he also kind of discovered or predicted pair production, the positron, which just a few, well, I think months or years later was actually discovered. Yeah, so vacuum is not as empty as the name suggests, but rather, as indicated behind me, there's a constant creation and annihilation of pairs, in particular electron and positron pairs, which are the lightest particles. Well, when Euler saw that, Euler, a student of Heisenberg, he realized that these, this pair creation and annihilation would give rise to nonlinearities, to photon-photon scattering. So if detection efficiency is good enough. So as you can see, what I indicated here actually is that you would apply a strong field, and these kind of align these pairs that you see behind me. So they are not randomly oriented as they were without the field before, but now they are kind of aligned, and therefore you get an idea why vacuum can get birefringent if vacuum is polarized by a strong field. In some sense, it's the same thing as what you would demonstrate in an beginning students lecture, where you would stress some, say, piece of glass behind two cross polarizers, and you would see the stress. Now we stress vacuum and expect in principle the same thing. So quite a fancy thing. So this was well, an important step towards quantum electrodynamics. And for quantum electrodynamics, you know, one of the important names is Julian Schwinger. And well, if we talk about the creation of pairs, then one question that we could ask would be, what is the lifetime of these pairs? Yeah, and we just calculated by energy time uncertainty. If we have a pair, then we have 2 times 0.5 mega electron volts, so the rest mass energy. And so we would say that this is h bar or h/2 or something. Yeah, and this gives rise to a lifetime of well, of femtoseconds or so, right? And now the idea is that we could make, and this will lead to the Schwinger limit, that we could make these virtual pairs real by accelerating them so strongly that they gain their rest mass energy within this lifetime, actually, right? And this is an easy back at the envelope calculation, and what you get is this thing here. That consists only of constants of nature and corresponds to, well, an enormous intensity that is not in reach so far. There's one thing that's interesting here, namely that we have here the ratio of the mass of these particles and their charge. And now there are speculations, as most of you might know, that there are yet undiscovered particles, perhaps lighter particles than the electron and the positron. And so they might have, well, if they have the same charge, they might have a much lower Schwinger limit, such that they can be more easily be created. Of course, this intensity is very, very high. And so what it means is this Schwinger limit. So actually, Schwinger just gave his name for that. Yeah, it was named after him. I think he didn't derive it on a paper, but nevertheless. So the Schwinger limit is the intensity where vacuum starts to absorb light. Yeah? And well, when there's absorption, there's also dispersion, as we all know. And so instead of looking at absorption, we can also look at the dispersive branch as indicated here, right? And then we would have a refractive index of vacuum, different from 1, as you see here. And it depends, of course, on the polarization, because these particles are aligned. And these are the formulas that are known from literature. And from this, well, I see this is the critical or the Schwinger intensity, right? So it depends on this ratio of the intensity that you apply and the critical intensity. And you see it will be a small number, because what we can reach is perhaps something like 10 to the, well, 21, 22. You'll see it will be more like 10 to the 20 for technical reasons. And of course, therefore, we have a phase difference between the perpendicular and the parallel component. And this means that vacuum becomes birefringent. And if one puts in all these numbers and expresses that in kind of natural units, so petawatt per square centimeter, then this is the formula. Yeah, and it is clear the longer the interaction lengths, just like in optics, the stronger the effect, but also the shorter the wavelengths, the stronger the phase difference between parallel and perpendicular polarization. Yeah? And therefore, the idea is that we would use a strong laser, ideally 10 to the 22 watts per square centimeter or so, and collide it with X-rays. And it is clear that this will be a femtosecond laser, and if we want to have good spatial temporal overlap, then we also should use a short pulse X-ray beam. So it will turn out that we need to have an X-ray laser. Okay, so this is the idea, yeah, and of course both are have a relative polarization of 45 degrees. So the idea would be the following. So we use this strong laser pulse here. So this petawatt laser pulse, it polarizes vacuum, and then we collide it with an X-ray laser pulse, and we would probe and we would put the thing between two crossed polarizers, right? And we would hope that we induce a little bit of ellipticity, as shown here. And therefore, a few photons will be transmitted and could hopefully be detected. Yeah, so this is the idea. Well, the idea Well, I should mention that this was first in this reference below by Tom Heinzel and colleagues. This was first calculated and proposed. But I guess, so this specific experiment, but I guess that they were inspired by another experiment that does pretty much the same thing, not with X-rays, but in the optical regime. And instead of using a short wavelengths, they use optical wavelengths, but they have a long interaction length. So this is the PV-LAS experiment, and it was originally proposed or started. I don't know the history of that experiment very well. So around 2000, and it is an experiment that is still active in Italy. Yeah, so Zavattini, the two Zavattinis, they are, to my knowledge, the central figures of that experiment. I never met them, so I can't say details about that. So now let's look at this formula and see what it takes. Right, so you see that you see this formula that I have written down before. Right, now we assume an interaction length of say 5 micrometers, which is approximately corresponds to the pulse duration. Right, and wavelengths that's typical for X-rays, and this number is just a the product of all these constants that we saw in the formula. And here I use something typical, so 20 zettawatt, so meaning 2 times 10 to the 19 watts per square centimeter. Right, and what we then get is a delta of 10 to the minus 6, as you see here, and the transmission is proportional to the square of delta, and so we get a transmission of a transmission of 10 to the minus 11. So from 10 to the 11 photons, there's just one that will be flipped in its polarization and detected. Right. So what this means is that we need a polarization purity, so that we really need an extinction ratio that corresponds to that number. So a polarization purity of this order of magnitude, and ideally we also should have a strong and intense X-ray laser, such that we have something on the order of 10 to the 11 photons per laser shot, ideally per minute, per day. It depends on how much beam time you have on the X-ray laser. Okay, so it takes a free electron X-ray laser. There is now one in Germany. There are of course others in the world. So here are a few pictures of that. So this is there, and we need a petawatt laser. Well, and this is kind of the approximation that we have in Hamburg for a petawatt laser. It's just 300 terawatts. If this would be 3 petawatts, we would be in much better shape. But of course, one has to use what one has. And these are the parameters of this system. Yeah, better than nothing, but not quite a petawatt laser. And as I said already, we need superb X-ray polarizers, and here you see one. So it's just a piece of silicon into which a trench is cut. So therefore, these are called channel cut crystals. A channel is cut in the crystal, gives a channel cut crystal. So this brings me to the next point: X-ray polarimeters in a nutshell. So what one does in order to polarize X-rays is that one reflects them by 90 degrees. And this is another experiment that you know from your introductory physics classes. If you scatter by 90 degrees, then the scattered radiation is polarized, just because electromagnetic waves are transversal waves. Now, so this is the same thing why at sunset the zenith of the sky is polarized because photons coming from there are scattered by 90 degrees. And this here is a nice fisheye picture of that. Now, so you see the sun here at the horizon, and you see the polarized light. I stole it from Wikipedia, I guess, yeah, as usual. Okay, so how do we scatter at crystals, at silicon in this case? Well, of course, Bragg scattering. And this is what you see here on this graph here. Yeah, so that we adjust the wavelength such we can choose it freely at an X-ray laser, right? That we adjust the wavelength such that the Bragg angle is 90 degrees, so that we scatter at 90 degrees, right? And because doing this a few times, one uses this channel cut crystal because one can then do the same thing, well, 2 or 4 or even 6 times and suppress the pi component further and further. And then such a polarizer would look like this, yeah, consisting of a polarimeter, I should say, consists or looks in principle like this, consisting of a polarimeter and an analyzer. Yeah. How are they made? Yeah, so this is actually, they are made by Berit Marx-Glovner in my group, and she was actually the first to start X-ray polarimetry in my group. It starts with an ingot, yeah, so silicon ingot here, and then one has to do good handcraft. Yeah, so they are thawed, they are oriented, they finally they are polished. Yeah. Quite an elaborate procedure in order to produce these channel cuts. And Berit is, of course, a master in this. Well, do they work? Yeah, so this is kind of the experiment that one does then. So you see that one would rotate the analyzer as one would do in the optical regime also, right? And then measure the transmission at a detector here behind the analyzer, right? And this was kind of our first experiment. Yeah, so you see this on a logarithmic scale. Yeah, so you would expect, of course, a sine square-like behavior, but on a logarithmic scale, it looks like this, right? And you see these many orders of magnitude that we achieved actually pretty much in the first experiment that we did at the ESRF at that time. So about 10 years ago or so, 11 years ago. Yeah, so a polarization purity you don't find in the optical regime, a polarization purity of 10 to the minus 10. Okay, well, what we had with this was an improvement of the art of X-ray polarimetry by about 2 orders of magnitude, and it is natural as a physicist to conclude that one can also do other things than such fancy things like vacuum birefringence. And so we set out for a few things, and the first thing that we did was to redo a classic optics experiment in the X-ray regime. So this is François Arago, one of the great French physicists, was also an influential politician actually, and a co-worker of Fresnel. And he discovered optical activity in quartz. Yeah, so found that the rotation, the polarization plane is rotated depending on the crystal symmetry in the one or in the other direction. And perhaps even a little bit more intriguing, a few decades later, Louis Pasteur, he was analyzing tartic acid under the microscope, and he was wondering actually that artificial thallic acid doesn't show optical activity, whereas natural one shows optical activity. And so he looked under the microscope at the crystals of artificial thallic acid and discovered that they are crystals that are the mirror image of each other, and he sorted them under the microscope and then did the experiment, and voila, there was optical activity in both directions. That's a really nice thing. And so we decided to use sugar in order to find optical activity in the X-ray regime, right? So this is kind of the experiment. Polarizer here and the analyzer here, and in between, not shown here, the sample, in this case a cuvette with sugar. So here are a few pictures. What you see here is the channel cut mounted on a goniometer. So here a closer look at this channel cut. Nicely can see this this crystal with the channel cut in. And here the analyzer. Of course, one also needs to rotate it around perpendicular to the X-ray beam, and here's the result. So there was a tiny effect. So 1 arc second of shift, 1 arc second of polarization rotation. We're quite pleased to find this effect, and also to show that the sensitivity of the instrument is so high. So meanwhile, there are quite a number of other applications, in particular with respect to nuclear resonant scattering, because their polarimetry is a very good method in order to suppress the background photons with 10 orders of magnitude or so. Actually, most of the times a little bit less, because for nuclear resonant scattering, you have to choose the wavelengths such that it matches the Messbauer line. But anyway, so these are the applications, and meanwhile, also something that we are kind of proud of is that there are now user instruments at DESY and also at the European XFEL. I think it's still under commissioning. I'm not sure whether it's already available to users. This is at the MIT end station. Okay, a few more things. So I said 10 to the -10 polarization purity. What are actually the limitations? Can we do better? Okay, and the first one is what's called Umweganregung. So here you see 2 planes, and the wavelength is chosen such that the deflection is by 90 degrees. But of course, this crystal has many other planes, and it may happen that the incoming beam is reflected here at this orange plane here, say, and then again reflected at this green plane, such that it has the same, such that it also goes in the same, such that it goes in the same direction than the beam that we want, right? So you see, this beam takes a detour, in German Umweg. So there is detour excitation. And of course, none of these reflections is by 90 degrees, and there is no suppression of the pi polaris, of the pi component. And therefore, this beam here is not polarized, and it would disturb the polarization purity of the beam that we want. So this has to be avoided. So we need to avoid Umweganregung. Well, it is pretty clear what one can do here. One can rotate the crystal a little bit around its azimuthal, so can change the azimuth of the crystal, and then this doesn't happen. But but that's not quite enough. So here you see Kai-Sven Schulze, and in his PhD thesis, he found a solution to the problem. Namely, he discovered that certain highly symmetric reflections, that for certain highly reflective reflections, all the Umweganregungen interfere destructively, such that the polarization purity is for these highly symmetric reflections, and silicon 400, which was one of our favorites, such that Umweganregung isn't a problem. Of course, you have to find this azimuth very accurately and to align it very accurately. And we devised meanwhile a method. Willy Hippler, whom you saw in the list of authors in the beginning, found that in his master thesis recently, how to align also the azimuth of a crystal quickly. If you do the same thing for 800, still a highly symmetric reflection, then this kind of funnel gets much narrower. So it's much more complicated to align, but still possible. So the other fundamental limit is actually the divergence of the X-ray beam, because if you have a divergent beam, then the beam consists of different k vectors, and of course they have slightly different polarization, just for geometrical reasons. And for synchrotrons, the divergence is typically 10 microradians, and just this limits the polarization purity to the level of 10 to the minus 10. We had these 10 to the minus 10 pretty quickly, and then things went slowly. So we had a hard time to improve it further until actually Kai-Sven Schulze found out in his dissertation that besides Umweganregung, also the divergence plays a role. But of course, X-ray lasers, so it's fully coherent, spatially coherent light. So there, the divergence doesn't play a role. We tested this actually at the synchrotron by limiting the divergence, by changing it artificially, so to say. And actually, what's also remarkable, or was remarkable about that experiment, that we used diamond as a material, and actually it turns out that diamond will probably be the best candidate for finally doing these experiments for different reasons. One of them is the heat conductivity and resistance to X-ray damage. So this is actually shown here. So depending on the horizontal divergence, we were able to reduce the purity and compare it to the theoretical limit. And you see that first of all, the smaller the divergence, the better the purity, and it matches to what we derive theoretically. Okay, now a first experiment at the European XFEL. It's already 2 or 3 years ago, and the XFEL at that time was still running in SASE mode, so no self-seeding yet. And we used it for the 400 reflection, which is at 3.5 kilo electron volts. So there's a lens here, which is important for the divergence, for adjusting the divergence. Then a few mirrors, then it's monochromatized, and this is our setup here, polarizer and analyzer, and of course the detector behind. And the divergence in this case was not 10 microradian, but just 0.3 microradian. And if one For the horizontal one, the vertical actually even better. The theoretical limit then would be 10 to the minus 13 for the polarization purity if it is only limited by divergence. But you'll see it's actually limited by something else. So here two photos of this thing, and here the extinction curve. Right, so you see it goes down to the level of 10 to the minus 11 or so. And the interesting thing here, so we zoom into this here and show the counts on the detector. And if you, so here, so it's just 0.01 degrees here. So this thing here. And when we are at the extinction position, then we don't detect any photon. So what we do with our polarizer is that we completely extinguish the free electron X-ray laser. Also, it has so many photons. And this limits the polarization purity that we can claim. So it is something like 10 to the 11, 5 times 10 to the minus 11. But it could also be 1 order or 2 order of magnitudes better. We just don't know because we don't have, or we didn't have enough photons for that. Okay, well, another thing that I didn't mention so far, right? We also need not only to match time, but also space, right? So what we also need to do is not only focus the laser beam, but we also need to focus the X-ray laser beam. So we need some lenses in between. And of course, these lenses should not change the polarization. We worked a while on that, and then together with Dr. Last from Karlsruhe, we found a solution for it. There may be other solutions, so we are still working on that. But this is another important thing, to build an X-ray telescope that doesn't disturb polarization. There's another interesting application now. You could use this as a confocal polarization microscope, a confocal X-ray polarization microscope. We did an experiment on that. I should have cited it here, but I forgot it. Okay, last point in my talk. How many days of X-ray of XFEL beam time will it take? I can't give you a definite answer on that, but I can tell you something about the scaling. So we need 5 sigma. Otherwise, people won't believe us that we detected vacuum birefringence, right? What you see here is the distribution that you would get if you do many experiments, and you just record the background. So if the petawatt laser is switched off, right? And the width is, of course, so if you have enough counts, background counts, then the width is the square root of this background number. And then if you apply the laser, then you would get a few more photons. You would detect a few more photons. So this is so these are the background photons, and this is the probability, and you would multiply it with the number of X-ray laser pulses. And when the laser is on, you would get a few more, delta and more, and you would have this probability here that you can calculate by the formula that I showed, or at least estimate in this way, right? And what we need is 5 sigma. This corresponds to this equation here, and if you solve it, then you find that the number of pulses must be greater than 25 times. So this is the square of 5 sigma. So if you want, if you are satisfied with 3 sigma, this would be 9. And then the background so the probability for background photons, which is pretty much the purity of your polarimeter. So you could say, so if the polarimeter has a polarization of purity of 10 to the minus 11, so this would determine this number here. And of course, the probability to see a signal photon, so a photon with flipped polarization, this strongly depends on the petawatt laser. And the question is, how does it depend on the parameters of the petawatt laser? And if you figure it out, so that it goes with the square, so the number of pulses that you need, that it goes with the inverse square of this detected signal photons, this gives rise to some remarkable scaling. And this is what I want to show here. So it goes linearly with the polarization purity. But here there's well, I should go to this side here. So the F number of the parabola that you use in order to focus your petawatt laser beam. So it goes with the 8th power of that, right? Well, it also goes with the 4th power of the pulse energy of the petawatt laser. So this is where you see how much it hurts that this well, petawatt laser, sub-petawatt laser at the European XFEL is well, unfortunately not a petawatt laser, but just a multi-hundred terawatt laser or so, right? So what one also sees is that longer X-ray pulses are actually beneficial up to the point where so what you basically need to do is to match the pulse duration of the X-ray laser pulse and your petawatt laser pulse in order to optimize things here. So the X-ray laser pulse is actually broadened by the polarimeter because it has a finite bandwidth of 80 millielectron volts, and more importantly, it is the penetration of the X-rays into the crystal that lead to a lengthening of the free electron X-ray laser's pulse duration. And one should match it, so it has then 100 femtoseconds. One should match it to the petawatt laser, otherwise one loses actually with the square of the pulse duration. Also quite interesting. But of course, the most important thing is to focus tightly and to do this and to put as much effort into this as possible. Okay, there are some newer ideas by my colleague Matt Zepf and Felix Karpstein, and there the idea is to suppress actually this these background photons even more by using an idea that is familiar from high harmonic generation, namely that you make a shadow here in the X-ray laser's beam, such that the signal photons that you can, so that the signal photons, at least those that are scattered in direction of the X-ray laser beam, that they can be discriminated from so from the background of the X-ray laser beam, right? And there's even what is even nicer about this idea is that if one now detects not only the flipped photons, but flipped photons, I say, if one detects not only the photons scattered such that the polarization is flipped, but also those that are scattered such that the polarization is parallel. So with the regular setup, you could never measure that because of the huge background. Then you can actually normalize out this huge dependence on the F number of the and other parameters, experimental parameters. Now, so because one side aspect or one corollary of this huge dependence, for example, on the F number is that it would hardly be possible to do any quantitative measurement if the effect depends so strongly on a single parameter like the F number. But if you so dividing the yield of the perpendicular polarized scattered photons and parallel scattered photons, this gives direct access to constants that are in the formulas that I have shown a little bit superficially. So this would then make possible quantitative measurements. Okay, so let me come to the conclusions. So it seems that we are now at a stage where high energy physics with lasers might start. It would be a cool thing if a laser experiment could discover a new particle. Maybe. So if it turns out that the birefringence of vacuum is stronger than predicted by QED, so that version of QED that only assumes the existence of the known particles, then and one makes that, one proves that with 5 sigma, then this would correspond to the discovery of a particle, at least a strong hint to us to a new particle. Precision polarimetry, I think, is now ready to take on the challenge. There's certainly still some work to be done, but nevertheless, it seems that it's possible. And of course, there is an unexplored number of additional research opportunities that have nothing to do with these, well, kind of esoteric kind of experiments like QED experiments. With this, I thank you for your attention.